In the previous module, we have introduced the complex exponentials. We have also seen the periodicity of complex exponentials. Before that, we have seen the systems that are linear as well as time invariant, and we have convinced ourselves that the LTI system, or the systems that are linear as well as time invariant, are of utmost importance just because most of the real life systems can be modeled using linear and time invariant systems. Now that we are aware of LTI systems and complex exponentials, let's look at the interaction between these. Let's have a system that is linear as well as time invariant. So if you have a system that is linear as well as time invariant, that is LTI system, let this be the input, that is x of t, and the output, let it be y of t, and the system, let it be represented by h of t. Let's analyze this system by giving the input as complex exponentials. A very important property of complex exponential is that the complex exponentials act as eigenvectors of LTI systems. Meaning, let's suppose we are having a complex exponential. So in general, the complex exponential is expressed as e to the power j omega t, and let's assume that there is a constant here, let it be a. If we give this complex exponential as an input to this LTI system, the output is the same exponential e to the power j omega t with a change in the amplitude. So let that change be denoted by a cap. This is the property of the complex exponentials. So it's very interesting that if we give a complex exponential as an input to the LTI system, the output is going to be the same exponential but being scaled by some factor. Let's prove this. Let's suppose I'm having a linear as well as time invariant system as has been shown in this figure, and we know that this LTI system is characterized by the convolution formula. So let's represent this LTI system, or the relationship between the input and the impulse response, by the convolution sum. So we have convolution sum as y of t equals to integration from minus infinite to infinite x of tau h of t minus tau d tau. And we know by the property of commutativity we can exchange the rules of x and h, so we can obtain minus infinite to infinite. This is equivalent to h of tau into x of t minus tau d tau. Now we are feeding this complex exponential as an input to the LTI system. That means x here is the complex exponential. So this one is x of t. So let's give this x of t, that is the complex exponential, as an input to this LTI system and see what are the changes that happens in this formula. Let me make some space here. So if we have this x of t as an input, we would get integration minus infinite to infinite h of tau x of t minus tau. So this will be replaced by a times e to the power j omega t minus tau d tau. We have simply replaced the x here by the input, that is complex exponential. This turns out to be equals to, you can see that this integral is a function of tau. So we can simply separate this out and take this e to the power j omega t outside the integration. So we have here as a, that is constant, has been taken out of the integration, and e to the power j omega t has been taken out of the integration. What we are left with is integration minus infinite to infinite h of tau e to the power minus j omega tau d tau. Now let's look at this equation. Now this part here, the integration of h of tau into e to the power minus j omega tau, let it be represented by some function. So let this be capital H, and as we know this is a function of omega, so that is going to be a function. After evaluation it is going to be a function of omega, because after this integration this h of tau is going to be replaced by the limits of the integration, and whatever that may be is to be evaluated at this omega, this particular omega. So let this be denoted by capital H of omega. So we can represent the same equation as, this is equals to a times, I'll write the h of omega first, into a e to the power j omega t. And we can see that from this expression that we have obtained that the output is the same as that of the input, but the only change here is this scaling factor, or the amplitude here is changed. So here we are indicating this as equals to a cap of e to the power j omega t, where this a cap is the changed amplitude or the new amplitude, that is a times h of omega. Very interesting. That means if we give a signal that is a complex exponential as an input, at the output we are going to get the same complex exponential, in fact with the same frequency, that is the same omega. The only change that would happen to this complex exponential is the change in the amplitude. And what would be that change? That is well-defined function, that is the integration of h of tau e to the power minus j omega tau. And assuming that this integral will converge, this would result in the change in the amplitude, but the frequency or the complex exponential frequency would remain constant. This property of complex exponential is called as Eigenfunction property. So let me write that. This means that complex exponentials are Eigenfunctions of LTI systems. Meaning, if you give a complex exponential at the input, you'd get the same complex exponential at the output. The mere change would be only to the amplitude of the complex exponential. Very important property of LTI systems with respect to the complex exponentials. And here this Eigen indicates, Eigen is a word that meaning of the Eigen is within or self-reflection. So this output is simply the reflection of the input but a change in the amplitude. That's why it is called as an Eigenfunction. And the amount by which the input gets scaled is called as the Eigenvalue. So h of omega here is the eigenvalue. This is the eigenvalue. Or the amount of scaling factor by which the input is getting scaled. So what we have seen is that the complex exponentials are the eigenfunctions, meaning if you have an LTI system, let me consider that once again. If you have an LTI system, and if you give complex exponentials as input, we get the same complex exponentials with a change in the amplitude. So I'm drawing this figure once again. And let's suppose if we are giving some complex exponential as an input, say a e to the power j omega t, we'll get the same exponential as an output, that is e to the power j omega t, but there would be a change in the amplitude, and that change is well defined as h of omega. Now let's analyze this. If we have given a complex exponential, we are getting the same complex exponential. Now as this system is linear, if we give multiple such exponentials as an input, we must get multiple such exponentials at the output. Meaning, let's suppose if we are giving a complex exponential with a specific frequency, let it be omega 1, and with a specific amplitude, let's say a1, at the output I should get the same omega 1 and a1 being scaled by a factor of h omega. And let's suppose if we are giving another exponential, let's say a2, e to the power j, let's say for a different frequency, we should get the output as h of omega. Now this must be evaluated at omega 2, whereas the earlier one should be evaluated at omega 1 times a 2 e to the power j omega 2 t. And like such, we can give multiple such inputs, and accordingly we would get multiple such outputs. As the system is linear, you can see that this system is linear. A combination of such inputs would lead to the combinations of such outputs. Meaning, let's say if you have the input as a linear combination of various such complex exponentials, so in general it would be a k e to the power j omega k times t, where this k is running from, let it be all the way from minus infinite to infinite. This is going to give you the linear summation of the corresponding outputs. So that is going to be k from minus infinite to infinite, h of omega k ak e to the power j omega k times t. So very interesting thing here. Just because this system is linear, a linear combination of complex exponential would lead to a linear combinations of this exponentials with the scaling factor of h omega. And you should note that here the output is being scaled. If we are giving individual complex exponentials, we are getting the same exponentials but with a scaling factor that is being evaluated at the frequency of the input signal. So we have written a general equation of what would be the resultant output if we give multiple such complex exponentials as input. So this would be true only if the system is linear as well as time invariant. Let me emphasize this equation that we have obtained, and we are going to see more into this in the next module. The point to note here is that the complex exponentials act as eigenfunctions of LTI systems, meaning if you give complex exponentials as input, you will get the same complex exponentials. The only change will be in the amplitude. We shall look more into this in the next module. Thank you.